Hi everyone, my name is Andrea, and today I would like to talk to you about the experiment that I've been working on for the last couple of months, which is the prostate energy diffusion quantum using PVP water solution. Now, before we start, I'd like to go through some questions. What is diffusion? What is a nonlinear gradient, aka an NLG, and what exactly is a phantom? So, with the term diffusion, what we mean is the random movement of water molecules inside tissue. This movement is random, it's called a random Brownian motion, but of course it depends on the characteristics and nature of the tissue itself. For example, as you all know, tumors and cancers, especially prostate cancer, has a very densely packed tissue. It's made of a lot of cells that are densely packed together. This inhibits the movement and diffusion of water molecules. And this is the difference that we can achieve. We can put in a spotlight to see between the difference of a healthy tissue and a prostate malignant tissue. So just to give you an example of what a DWI image looks like, this is, here we have 5 DWI images and an ADC map, ADC standing for apparent diffusion coefficient. So as you can see here, the DWI images allows us with brightness to distinguish between tissues that have a similar diffusion pattern or a high diffusion pattern or a low diffusion pattern. These images can then be put together and quantified to create an ADC map, which is what you see here in the bottom right. But how exactly does MRI work? In MRI, we have, as I said before, in a tissue, we have a random movement of water molecules. We first apply a magnetic field known as B0, thanks to the MR scanner, which gives a net magnetization of the tissue itself. This net magnetization puts most of the water molecules in a state of equilibrium. In this case, it's like pointing upwards. After the water molecules reach the state of equilibrium, we then apply a second gradient, which tilts the water molecules first by 90 degrees and then by 180 degrees. This second pulse, 180-degree pulse, completely undoes the first 90-degree pulse. So we're able to see if in the meanwhile, water molecules have moved or if there was a spin in the water molecules. The gradient itself, the gradient is what the machine applies, can be defined as a magnetic field in which the Larmor precession or Larmor frequency is different at different locations. So imagine a water molecule inside a room that's packed with obstacles and objects and furniture and so on. This water molecule cannot move, cannot spin, and is basically constrained in the position where it is. Now, we excite the molecule with the gradient that we give it, first by 90 degrees and then by 180 degrees. If the water molecule hasn't moved at all, we expect the second pulse to completely undo the first one. We expect the 180-degree pulse to completely undo the 90-degree pulse. And since the water molecule hasn't moved at all, the spin that it had before is perfectly aligned with the spin that it has at the end of the experiment. And since it's perfectly aligned, we expect the maximum signal. So the pixels will be very, very bright. On the other hand, if there is diffusion inside the tissue, if the water molecule is actually able to wander and roam around the room because maybe it's filled just 50% or 40% with furniture, in this case, the water molecule is able to move and spin. So after we apply a 90-degree angle pulse, before the 180-degree, the water molecule will spin a little bit. And this is what creates a magnetic current that is then detected by the MR scanner and gives us the image. So this spin, before we apply the 180, this angle that is created is what allows us to understand what's inside the tissue. So the spin just approximately returns to the x-axis, but it's not perfectly aligned. Therefore, we have a loss of signal coming from the water molecule, and this results in pixels getting darker. So we can now differentiate between pixels, dark pixels and bright pixels, which means water molecules that can actually diffuse and can move around the tissue, and water molecules that cannot move because they're constrained. And this allows us to differentiate and distinguish between a tissue where there are just a few cells or maybe tissue with a lot of cells densely packed, such as the tumor. Now, imagine we use a stronger diffusion gradient. In this case, we allow for a greater degree of randomization of direction, greater signal loss, and therefore a greater sensitivity to diffusivity. So if we can use a stronger and with more magnitude gradient, where it allows us to be to get more sensitive to diffusivity images, therefore to distinguish more easily between benign and malignant lesions. Second question, what is a gradient in DWI? As said before, the gradient is a magnetic field in which the Larmor frequency or precession is different at different locations. Now, in order to achieve this stronger gradient that I was talking about here, we need to increase the B value. How can we increase the p-value? The p-value depends on 4 variables, as you can see here, which are gamma, g, which is the magnitude, lowercase delta, which is the duration, and uppercase delta, which is the time interval. Gamma is just the barometric ratio of the molecule itself. So in order to increase the p-value, we can either work on the g variable, which is the magnitude, or the delta, which is the time. As you can see in the paragraph below, in the graph below, we can either increase the g to get a higher p-value, which is the area basically of the rectangle, or we can increase the delta, which is the time duration. In both cases, we get a higher p-value, but there is a trade-off, because by increasing the delta, which is the encoding time, we're starting to lose signal, because molecules start to relax, and therefore the image gets noisier. So a stronger gradient equals a better image, but at the same time, we have to keep the encoding time as short as possible to allow for a higher resolution. Unfortunately, linear gradients cannot achieve very high G, very high amplitudes. Therefore, in order to get a sensitive to diffusivity DWI image and an ABC map, we have to increase the delta. We have to increase the encoding time. But as I said before, this only allows us to get very low quality images, even though it's very sensitive to diffusivity. This is where NLG come into play. NLGs allow us to concentrate the field change in just a small region, as you can see here. With the linear gradient, we have the same strength all across the field, 50 centimeters, 100, 150. But with the non-linear gradient, what we have is a very strong gradient here, just in the beginning, in the region that we're interested in, and then a reduced gradient strength in the rest of the part. But we're not interested in that. We're only interested in the part that we're going to analyze, which is the prostate in this case. So by doing this, we can reach very high Gs, very high G value without having to increase the encoding time. So the benefits of NLGs are it can concentrate the field change. It works very well on the prostate, especially because it's small, it's close to surface, relatively isotropic, but it works very well also on the breast. It has high SNR, which stands for signal to noise ratio, allowing for a high resolution of the image. Therefore, shortening encoding times and higher B values increase the ability to distinguish between benign and cancerous lesions, which is what we're looking for. So let's compare these two images. As you can see here, we have a T2W image and ABC map that has been obtained by DWI images. As you can see in the T2W, the quality is very high because it's very high resolution. We can distinguish all the different organs, but at the same time, it's very difficult to distinguish between benign and unhealthy or cancerous tissue here in the prostate, which is supposedly here. On the ADC map, however, we can clearly distinguish between the two types of tissue here. But there is a trade-off, because as you can see, the quality here is completely different from the first image. It's very low quality, but at the same time, it allows us to distinguish very well between benign and prostate lesions. So what we're trying to do with NLGs is get both a very high resolution and a very high sensitivity to diffusivity to allow for an early diagnosis of benign and malignant prostate lesions, saving unnecessary procedures such as biopsies. So this is our NLG. This is one that we use. Normally, an MR scanner is a machine that looks like this, with the internal board that produces the magnetic field. In our case, the magnetic field was produced by the gradient coil that sits inside the scanner itself with the patient, so that the coil is right in front of the prostate. So, as you can see here, the legs are resting here with the prostate right in front of the coil, which allows for a much greater gradient. Lastly, what is a phantom? A phantom is just a specially designed object that is utilized as a stand-in for human tissue. Basically, what we wanted to recreate is a solution that can mimic in the best possible way, I don't know where this is going forward, in the best possible way, the prostate tissue. Okay, now that we've gone through all of that, what do we do with that information? The purpose of a study. The purpose of a study was then to validate the feasibility and accuracy of DWI and ADC mapping using NLGs that are designed to provide a high grade in the prostate. This is what I've been telling you. This could help distinguish between malignant and benign prostate lesions, thereby saving patients from unnecessary invasive procedures such as biopsies. So the first step of the experiment was designing the phantom. The phantom was designed in two parts. First, we designed an arch-like structure, and then we designed a box that could be attached to the first part via plastic bolts. This allowed for an easier switch between phantoms. So if in the future we want to use the same arch-like structure to sit on the same gradient coil, we can then change the box in shape, or maybe we want to change what's inside, and this allows us to switch between phantoms much easier. These are some sketches that I've drawn, both on my notebook and on the website that I use, which is Tinkercad. And the step 2 of the experiment was preparing the PVP water solution. PVP stands for Polyvynilpyrrolidone, and literature showed us that it's very useful in recreating prostate tissue because it's very cheap, it's non-toxic, and it's relatively isotopic. So we made 6 different vials with PVP water solution ranging from 5% to 50% to, oops, sorry. I don't know what's happening. Okay. I don't know what it's going for.
Yeah, I just asked Taylor.
Oh, okay. So in order to replicate and mimic the prostate tissue, we decided to use a PVP water solution with different PVP concentration from 5 to 50%. As I said, by doing this, we wanted to cover as much as possible the range of possible tumors that we might encounter. 5% being very low-grade tumors, 50% being very high-grade tumors, plus just a pure water vial in the middle. So the final result was, I don't know why, okay, this was supposed to be a joke. The final result was not this one, it's actually this one. I don't know why it's not working, it's going so fast.
Yeah, it's flying, guys.
Okay, this is final result.
You sure it's a joke?
Yeah, this is actually fine. Actually, if you want to take it, I brought it here with me just to show you. Oh. And also the other part. Yeah, this is the final result.
It's really a hardware work.
Yeah, 3D printed. And so step 3, the last step, was scanning the phantom. By scanning the phantom, we acquired DWA images with both the linear gradient and non-linear gradient, and this is the result. We obtained ADC maps from the DWA images, and as you can see, there is basically no difference between the images obtained with the linear gradient and non-linear gradient. This is what we were expecting. This is a graph taken from the Pierre-Pauli abstract. As you can see, we have an inverse proportion between PVP concentration and diffusivity. Of course, as I said before, imagine PVP as being an obstacle inside a room. If the room is filled with 50%, the diffusivity would be very low. If the obstacle is just 10%, then the diffusivity would be very high. Water molecules have room to move around the room itself. And this is what we got. With both the linear gradient and non-linear gradient, we can see we have an inverse proportion between diffusivity and PVP concentration. So we proved what we wanted to prove. The nonlinear gradient produced similar diffusivity results with different PVP concentrations to those produced in the linear gradient coil, but of course, work isn't done. Future research will have to demonstrate gains obtainable from shorter diffusion encoding times. I would like, before concluding, to thank all of you, especially the Alliance Center and the MRRC, where I worked at with Gigi, Nala, and Atesh, also the Wright Lab, and of course the ONAOSI Foundation, without which nothing would have been possible. Thank you.
Congratulations, one more case where you really build up the real stuff with 3D printing. It's amazing. Bonding, question.
The plot that you showed near the end of what you expected, I think at high concentrations it became nonlinear.
Exactly, yes. This is a very good question. This is also one of the reasons why we stopped at 50, if this is your question.
Yeah, I was wondering if you understood it, tried to go to those high concentrations.
Yeah, we stopped at 50 for different reasons. The most basic one is it's difficult to work with PVP because the solution gets very sticky and very viscous at high concentration. Even working with just the 50% has been a real challenge. So working with maybe even 60, 70 would have proved very, very hard. Secondly, as you can see here, the correlation between PVP concentration and diffusivity stops being linear after 50%. So it's non-linear. So it would be, I want to say, dangerous to try and recreate what they've done, because probably we would get a very different result because it's not linear anymore. And thirdly, the third reason why we stopped at 50 is because, as I told you before, we wanted to cover as much as possible the whole range of prostate cancer that might come up in a lab or in an MR scanner. And to do this, we decided to use 5% to 50% PVP solution, because 5% mimic very well low-grade prostate cancer, while 50% mimic very well high-grade prostate cancer. Usually, above 50% would mimic a prostate cancer that is very rare, that's not usually seen, and so all of this put together we decided that it was useless to go further, 50%, but of course it's a really good question, and maybe we can use in the future other materials, maybe not PVP, maybe we discover another new material that can allow us to broaden our spectrum of percentages even more. Thank you.
Very good. One more. questions? No? Everything was clear, very good,
Thank you.
congratulations.